Okay, let's look at some subsequences now. So, consider the sequence Sn defined by Sn equals -1 to the power of n times n. Now notice if we were to replace n with the value of 1, we would get, for example, S1 is equal to -1 to the 1 times 1, and that's of course equal to the number -1. So that's the first term of the sequence. Similarly, if we replace n with 2, we get +2, or n with 3, we get -3, etc. Now this sequence is pretty clearly not monotone. I mean, it is alternating after all. But some of the terms can be selected to make special sequences that we could sort of pull or cull out of Sn. Let's look at a couple of those. So, for example, consider S sub n sub k, where nk is equal to 2k for k in the natural numbers. So in other words, we'd be looking at k equals 1, 2, 3, which means we'd be looking at n sub k equals 2, 4, 6. In other words, the even terms of the sequence. Notice that if k were equal to 1, 2 times 1 would be 2, so the first subscript of the S would be 2, giving me the number 2. If we took the second term of this weird sequence that has double subscripts, then we would be saying that n sub 2 would be equal to 2 times 2, which is 4. So we'd be looking at the fourth term of the sequence, which is 4. And so on and so forth. We'd end up getting 2, 4, 6, ... Similarly, we could look at S sub nk, where n sub k was equal to 2k minus 1. So now if k were 1, we'd have 2 times 1 minus 1, which is 1, so we'd be looking at the first term of our sequence, which is -1. If k were 2, then the n sub k, the subscript on the S, would be 2 times 2 is 4, minus 1 is 3, so we'd be looking at the third term, and so on and so forth on that end. So notice that in both of these cases we were able to take this original non-monotonic sequence and find these take a few of the terms, or very specific terms, and create monotone sequences out of that original big sequence. Notice also, by what we talked about today, that since we have a monotone increasing unbounded sequence here, that means the limit is certainly going to be positive infinity for this first sequence. And in the second case, we would have a monotone decreasing unbounded sequence, so this limit would be negative infinity. Okay, if you couldn't tell, I'm trying to avoid saying the word formally, but now we're going to formally define what it means to be a subsequence. And that's of course what I was creating there before, were subsequences. So now formally, if we let Sn be a sequence, I'm subscripting here from 1 to infinity, or letting it go from 1 to infinity, and if we let n sub k be another sequence that goes from 1 to infinity, but the second sequence, this n sub k, is going to be a sequence of natural numbers, with n1 being less than n2 being less than n3, etc. Informally, we'll think of this as being a subscripting sequence, because it's going to pull certain terms from the original sequence. Okay, in this case we would call this new sequence, S sub n sub k, for k marching from 1 to infinity, a subsequence of the original sequence, which was the Sn's going from 1 to infinity. So informally, a subsequence is just like taking an original larger sequence and then pulling out whatever terms you want, as long as the terms are in order. So you have to make sure that you're going from left to right and you pull out whatever terms you want in order. Okay, this definition requires that the nk is increasing strictly, right? n1 is smaller than n2, is smaller than n3, etc. So that means that it is not possible in a true subsequence, even if this goes against maybe what you would informally think of as a subsequence, it's not allowed to jump around. No jumping around. Right? You have to only be able to go forward. So you can only go, there is no way to jump around back and forth. You can only go forward. Okay, let's look at an example real quickly here. Consider this big long sequence of 1, 1/2, 1/3, 1/4. So in general 1 over n, for n being subscripts or from natural numbers. Notice that we can look at t sub k, which is a sequence defined as 1/5, 1/6, 1/7, 1/8, etc. And notice how that's picking on this term and this term and this term and this term and so on and so forth. So since it's taking some of the terms from the original sequence, we would call t sub k a subsequence. And in this case, the tk's would be defined to be s sub n sub k's, where the nk has to start at term number 5 and continue on from there. So we notice that the nk's would be equal to k plus 4. Right? If k were equal to 1, we would get 1 plus 4, which is 5. And notice we took first of all the 5th term. If k were 2, then n sub 2 would be 2 plus 4, which is 6. So the subscript on the s would be 6, and that would give us the 1/6, etc., and etc. Okay, now look at the u sub k's. Here I have a sequence u sub k, which again takes some of the terms but not all. So it goes 1, and then it takes the 1/2, and then it takes the 1/4, and then it jumps out here to the 1/8. So it's also choosing some of the terms going from left to right. This is a subsequence also, and the uk's would be s sub n sub k's, where the nk's are being picked by a different rule this time. The rule this time is 2 to the k minus 1. Again, notice that if we were to look at n sub 1, the first subscript on the k's, then we would get 2 to the 1 minus 1, 2 to the 0, which is 1. So that subscript tells us to pick the first term and put it into our sequence. For the second subscript, n sub 2, we'd be looking at 2 to the power of 2 minus 1, which means we'd be looking at the 2th or second term and making that part of our subsequence. Now, if we were to look at the third term, 3 minus 1 is 2, 2 squared is 4, so now instead of picking the third term, we're picking the 4th term, and then we pick the 8th, so we're just getting a subsequence. Finally, notice that vk here, this is not a subsequence, because let me use orange to highlight this. This would go from 1, and then it goes up to 1/3, and then it goes back to 1/2. So immediately now it's not a subsequence, but even further on it goes 1/5 to 1/4, and then it goes 1/7 to 1/6. But since it keeps going back and forth and back and forth and back and forth, it is not going to be a subsequence. So it is not a subsequence because it jumps back and forth. Okay, now let's do a little practice problem. Let n sub k from going from 1 to infinity be a sequence of natural numbers such that nk is always less than nk plus 1 for all k. So it's just like a subscripting sequence. Wow. Okay, let's try to prove the claim that n sub k is bigger than or equal to k for all k's that are natural numbers. Okay, first step, let's go by induction here, of course, because we're trying to prove something for all natural numbers. And base case, well, notice that n sub k is a natural number. So n sub k is a natural number. So we know for sure that n sub k is going to be bigger than or equal to 1 for every k. So in particular, n sub 1 is bigger than or equal to 1, and that verifies the base case. What would a good induction hypothesis be then? That would be something like, suppose n sub, can't use k, let's go n sub l is bigger than or equal to l for some l in the natural numbers. Then, to jump up to the inductive step, we would notice something about n sub l plus 1. Right? Well, n sub l plus 1 is bigger than n sub l because we assume that it is a strictly increasing sequence. And by the inductive hypothesis, we know that n sub l is certainly less or bigger than or equal to l. So since these are natural numbers, what does that tell us? Well, the fact that n sub l plus 1 is bigger than l means that n sub l plus 1 is bigger than or equal to l plus 1. Right? Worst case scenario, it's right next to it. I definitely know that it's bigger than, so it has to be at least one step bigger than l. So n sub l plus 1 will certainly be bigger than or equal to l plus 1. So, by the principle of mathematical induction, done. And that one gets an MWO. Okay, so now that we know that fact, we can actually prove an interesting theorem here, that if S sub n converges to a real number s, that's not real numbers, that's, remember, if we have a limit, it's unique, so we're converging to a real number called s, then every single subsequence of Sn also converges to that exact same number s. Let's see if we can show this here. So let's suppose that Sn converges to s. Then, if we're trying to show that every subsequence also converges to s, this is a universal quantifier over subsequences. So let's let s sub n sub k be a subsequence of Sn. Okay, now we want to show a convergence statement, so recall our definition of convergence. Now we're going to let epsilon greater than 0 be given. We're going to have to choose a capital N, so let's look at it this way. Let's choose N such that N bigger than or equal to N implies that Sn minus s is less than epsilon. We can do this because Sn converges to s. So this is the definition of Sn converging to s. Okay, now what can we notice about that though? Well, notice that if k is bigger than or equal to n, we get that n sub k is bigger than or equal to k by that previous fact that we did, which is bigger than or equal to n. So not only does s sub n minus s end up being less than epsilon, but we actually get that s sub n sub k minus s happens to be less than epsilon. So if k is bigger than or equal to n, the n sub k is bigger than or equal to k by this practice problem, right here, and that's bigger than or equal to n, and that's going to force the s sub n sub k's distance from the limit to be less than epsilon. So s sub n sub k will also converge towards s, and we get an MW over here too. So that's really interesting. If a sequence converges, then that means every subsequence of it must also converge, and in fact it must converge to the exact same thing. Okay, well, interestingly, among other things, this theorem actually provides a pretty smooth and cool way to show that a particular sequence diverges. For example, consider the sequence we've seen before, defined by s sub n equals 1 minus negative 1 to the nth power. Recall this sequence right here happens to be what? Well, if we let n equal 1, we get 1 minus negative 1, so that's 2. And if n equals 2, we get 1 minus 1, which is 0, and then 2, 0, 2, 0, 2, 0, etc. Right? Well, notice that this has two pretty obvious subsequences. Notice that if we were to take the first, third, fifth, etc., we end up getting a subsequence that looks like 2, 2, 2. And that sequence converges to 2. If we take the second term and the fourth term, etc., we end up getting another subsequence of zeros, and this one converges to 0. Right? But look back real quickly. That means that we have that not every subsequence of Sn converges to this value of S, so therefore not the original sequence converges to S. So we end up having two different sequences. If we end up getting two different subsequential limits here, then there's no way that the original sequence could ever have converged. So that's a pseudo MWO, because I'm doing it more as like an example here. Okay, so now here is an important theorem. I highlighted in red important. You will want to remember this one for the rest of the lecture, plus from now on for probably the rest of your life. Every bounded sequence has a convergent subsequence all the time. Every time, no matter what. Okay, let's start off a proof here. Let Sn be a bounded sequence, and let T be the set of the outputs, the image values of all of the sequence terms. Now, just like a proof we did last time, we're going to go by a finite case, and then we're going to go do the infinite case. So in the finite case, what happens here? Well, notice that if there's only finitely many image points, then there is some x width such that S sub n is equal to x for infinitely many n's. Right? Because there's only finitely many different objects in T, so there must be one particular value that gets hit for infinitely many n's, because Sn is an infinite sequence, right? There's infinitely many terms in the sequence. Okay, so simply choose, since there's infinitely many, we can always go beyond any other term or any other term in the sequence that we've gotten so far, so we can just choose the n1 to be less than n2 to be less than n3, with each s sub n sub k equal to that x, because it appears infinitely often in the sequence. It has to appear infinitely often, so it keeps on going and going and going, and eventually coming back and back to x over and over again. Well, notice that this constant subsequence, right, this is constant because it's just always equal to x, does converge, right? In fact, it converges to x. So this constant subsequence converges to the value of x. So that concludes the finite case, right? We needed to show that we had a subsequence that converges, and since we have infinitely many x's, we can converge to x. We just keep choosing x and x and x and x again. Okay, so now the challenging part, the infinite case. So if T is infinite, we're going to go through Bolzano-Weierstrass again. So Bolzano-Weierstrass says that if we have an infinite, remember infinite and bounded, right? Infinite and bounded. Bolzano-Weierstrass says that T has an accumulation point. Accumulation point x. Okay, now for each k in n, let n sub k equal a neighborhood around this accumulation point of x that has a radius of 1 over k. So for each k, these neighborhoods are going to be swallowing up around x. So there's my number line, there's x, And so n sub 1 is going to be kind of a large one, but it's an accumulation point, acts as an accumulation point, so there's going to be a point in there, infinitely many points in there in fact. And then n sub 2 will be a 1/2 radius, but there's infinitely many points in there, and there, and there. So every time I make one of these neighborhoods, I keep getting infinitely many points inside of those neighborhoods. All right, so let's be formal. Let's make sure we state that. So since x is an accumulation point, that means there are infinitely many s sub n's in each n sub k, each one of these neighborhoods. So let's just define a sequence now. We will choose s sub n sub 1 to be really anything that's in A1, right? Any one of these elements from the sequence that are in the A1. And then to continue, we will, for each k plus 1, simply take s sub n sub k plus 1 to be an element in a k plus 1 with that forced increasing subscript that we needed to happen. So I'm just going to make sure that n k plus 1 is bigger than n sub k. And notice this is just always possible because there are infinitely many sequence terms inside of a k plus 1. So we just have to make sure we go out far enough and then we finally hit one that we want. Okay, what does that mean? Well, notice that now s sub n sub k is a subsequence of Sn, and not only this, but in the sequence we know that s sub n sub k minus x is less than 1 over k for all k in n. So for n equals 1 and on, we're always forcing it to be inside of this particular neighborhood, so we're making sure that we're always really, really close and getting closer to the accumulation point. So what does that mean? That means that S and K is going to be a convergent subsequence, and it's going to converge to X, and that's MWO. So remember, the statement of this is going to be that every single bounded sequence always has a convergent subsequence. Okay. Now, this is an on-the-side theorem. I think that the textbook proves it for unbounded above, and we're going to do it for unbounded below, because there's an extension of all these ideas to positive and negative infinity that's pretty natural, but just to make sure we're being putting in as many details as we need. A sequence that is unbounded below contains a monotone subsequence that definitely goes off towards negative infinity. Okay, we're going to prove this. Since S sub n is unbounded below, we will choose S sub n sub 1 to be something less than negative 1. Right? We're unbounded below, so we go as low as we possibly need to. So we're just going to make the first subscript on the S be some value that happens to go less than negative 1. Okay? If we suppose, if we already have n1, n2, n3, ... we will simply choose S sub n sub k. Oh, wait, sorry. If we already have values n1, n2, n3 up through nk, we will choose S sub n sub k plus 1 to be the minimum of the opposite of k plus 1 and S sub n sub k. Okay, we need to have this weird little minimum thing here because remember, s sub n sub 1 is less than negative 1. S sub n sub 2 will then be chosen to be at least as small as negative 1, and if we ended up going further, then we can at least get down to negative 2. We can force a negative 2 on there. Again, remember, it's unbounded below, so we just need to get as far as we need to down there. So s sub n sub 3 will be at least as low as negative 3, and s sub n sub 4 will be at least as low as negative 4. So in general, s sub n sub k plus 1 will be at least as low as the opposite of k plus 1. Okay, it should be pretty clear that this subsequence is always going to be less than negative k as k goes off to infinity. So this subsequence is bounded. Sorry, it's not bounded. Opposite of that, it is unbounded and decreasing. So, as we saw in the last lecture, its limit is negative infinity. And that proves it in this case. Read the textbook to see the unbounded above case, but really try to pause the video and see if you can figure this out on your own and fill in the details. It's approximately the same type of proof. Okay, now some new definitions. Let Sn be a bounded sequence, although the concepts, like I mentioned before, can be extended to unbounded sequences also. We will call a subsequential limit a real number that is the limit of some subsequence of Sn. So lots of different subsequences in there, and if there is a subsequence that converges, then we will call any possible convergent limit a subsequential limit. Okay? If we let S, capital S, be the set of all subsequential limits that exist, then we will define the limit superior as lim sup of Sn, and this will simply be the supremum of the set S. So in other words, it'll be the largest subsequential limit that exists. But remember, supremum, in case we get some kind of weird case where we have a non-maximum, something that's not inside of the set. And then, on the other hand, we'll define the limit inferior as the lim inf of Sn, and that will be the infimum of S. So although the notation is kind of similar here, remember that lim sup and sup are different ideas. The supremum was the least of all the possible upper bounds on a set of real numbers, which exists on any bounded set by the completeness axiom. Limit superior is the supremum of all of the possible subsequential limits of some given sequence, Sn. So similar, or they're related, of course, but they're not the same thing. Okay, clearly, right. And remember, when you hear something in math clearly, that means you should be able to justify it. But what happens if a sequence converges? Remember, at the beginning of the lecture, we said when a sequence converges, then all of its subsequences converge to exactly the same limit. Right? When a sequence converges, all of its subsequences converge to the same limit. Right? So in that case, the limit inferior of the Sns will always be equal to the actual limit of the sequence, which will be equal to the limit superior of the sequence. So if the limit exists, it's equal to the limit inferior and it's equal to the limit superior. Okay, so we have put a new definition in here now. So we'll say that a sequence is said to oscillate if, remember, we have these subsequential limits, and these subsequential limits are actually going in different directions, they're not the same, it's pretty clear that the limit inferior will always be less than the limit superior. So if the limit inferior is less than, not equal to the limit superior, we'll say that the sequence is oscillating. And just think like the O2, O2, O2 one, right? The O's would be a limit inferior and the 2's would be a limit superior, and those are different from each other. So that's what we'll be able to see here. Okay, so consider this crazy example. 1/2, 1/2, negative 1/2, 1/3, 2/3, negative 2/3, etc. You can see it written there. We're going to find, first of all, S, which is the set of all subsequential limits. So first let's find the blues. Okay, and by blues I'll underline some of these terms in order. So I'll take the 1/2 right here, the 1/3 right here, the 1/4 right here, the 1/5 right here, and if the pattern continues we'll get a 1/6 and a 1/7 and a 1/8 and etc. Right? Where does that sequence head to? Well, as n goes off to infinity, this sequence would limit of this sequence is equal to 0. So we have a subsequential limit of 0. Okay. Let's look at every third term starting with the second one. So we have 1/2, 2/3, 3/4, 4/5, etc., etc., etc. So what is this sequence? Well, that sequence is always one less than the denominator, so we're looking at an n minus 1 over n. Right? Actually, I guess the way I define it here would have to be not there. Didn't put this in my notes. We'd have to go n plus 1. Oh, there we go. n plus 1, because the first one would then be 1/2, and the next one would be 2/3, etc. Okay, that limit is 1, so we also have a subsequential limit of 1. Okay, finally, if we look at the third term and every third term, we have another sequence here which is essentially just the limit of the negative n over n plus 1s. And so that limit is just negative 1, so we also get a negative 1. Okay, so S, the set of all subsequential limits, and it appears that these are it, is that we're going to get 0, 1, and negative 1 as our subsequential limits. Okay, so remember the lim sup is the supremum of this set of subsequential limits. Well, that's a finite set, so the lim sup is actually just the maximum of these. What's the maximum? Well, that's 1. Similarly, lim inf is the infimum of the set of subsequential limits. So that's just going to be the smallest of these values, which is negative 1. So yay, that's how you can work with a problem, find its subsequential limits, and then create the limit superior and the limit inferior. Okay, let's make a picture. You know how I like pictures here. So let's try to see a picture of what's going on. Sn is a bounded sequence. We're going to suppose Sn is a bounded sequence, and we have this limit superior of Sn. Same kind of argument would hold for limit inferior, but we'll just look at the superior here. So m is kind of hanging out right here. Okay. Now, notice that in the red marking over here, that there cannot be infinitely many terms. Infinitely many terms out here. Because otherwise, what would happen? Well, if we had infinitely many terms out here in the red, because of the fact that it's a bounded sequence, then we recall that a bounded sequence with infinitely many terms is going to have a convergent subsequence, right? By that big theorem. So otherwise, there would be a convergent subsequence out here. But if it was out here in the red, then it would be above m plus epsilon for any kind of epsilon, right? Any epsilon that was given. So that won't work. That makes me think maybe that's unclear here. That this is just an arbitrary epsilon, so it's like saying epsilon bigger than 0. Right? So if we go out there, then we have to make sure that, well, there can't be any convergent subsequences out here, because if there were, they would converge to a number that would be larger than m plus epsilon, and then that means that m would not be the limit superior, because remember, m is the limit superior. It's the supremum of all of the subsequential limits. So in other words, up here, well, let me put this in red so we're being consistent here. Up here, there's only finitely many terms of the sequence. Okay. On the other hand, if we come down here to the orange, right, the orange is the stuff inside of this epsilon window around M, then in here there must be infinitely many terms of the sequence because otherwise, if this didn't happen, then we would not be able to find a convergent subsequence that would be inside of this orange window. So otherwise we would not have a convergent subsequence above m minus epsilon. And that's a problem because, again, remember, m is the limit superior. So if we didn't have any kind of convergent subsequence in here, then we would have a new m minus epsilon upper bound on all of the subsequential limits. And so the subsequential limit supremum, which would be the limit superior, would actually end up being lower. So in other words, inside of here, what we're saying is that in the orange there must be infinitely many terms. Okay, so that's what our picture is looking like. You might wish to pause and rewind this a little bit here so you can watch that again, because this is really the crux of the matter with limit superior and limit inferior, is that near we get infinitely many terms, but outside of near we get only finitely many terms. Okay, so that picture was an informal argument, or a picture type proof of the following theorem. If Sn is a bounded sequence and m is the limit superior of the Sn's, then we know that for every epsilon greater than 0 there exists a capital N in n such that n bigger than or equal to n forces S sub n to be less than m plus epsilon. So for every epsilon greater than 0, right here, there has to be a capital N such that I can go out that far in the sequence, and eventually I will be completely inside of here. There's only finitely many things out here in the red. And 2, for every epsilon greater than 0 and for every natural number, there must be a k bigger than that natural number so that S sub k is bigger than m minus epsilon. So that's like saying that no matter what, for every epsilon greater than 0, go down here to m minus epsilon, there has to, and for every natural number, no matter what natural number you choose, there's another term further along inside of the sequence that lands me inside of this window, because there have to be infinitely many terms inside of that window. So as a challenge, try a verify at home here and try to formalize the picture proof. Right, I gave the picture proof, and I gave the a description of what was going on inside of that picture. See if you can formalize it and actually write up a proof of this theorem that's formal, has all the details. Okay, as a corollary to that, though, after you try to formalize that, pause the video and try to formalize it here. Consider this corollary. Let Sn be bounded, just like in the theorem, and let m equal the lim sup of Sn. Then m not only was the limit superior, so it was a supremum of S, but it actually is physically inside of the set S. So if it's actually inside of the set S, in addition to being the supremum, that means it's not only a sup, but it's actually a max. Because remember, the maximum is actually an element of the set. So notice that this is actually pretty simple to prove here. The theorem above, and that's why it's a corollary, I guess, right? The previous theorem implies that for every k, there is an S sub n sub k such that m minus 1 over k is less than S n k is less than m plus 1 over k. Because the previous theorem said that this was going to be true for any epsilon that was positive. So in particular, it's going to be true for 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc. But what does this imply? Well, if you're in between m minus 1 over k and m plus 1 over k for every single k, that literally means that s sub n over k minus m is less than 1 over k, and so s sub n sub k is going to converge towards m. And since we found a subsequence that converges to m, that means that m is in the set of all subsequential limits. So get an MWO there. Okay, as a very last theorem to consider here now, let's this will be useful for a homework problem. Suppose that Rn converges to a positive number r and let Sn be a bounded sequence. We claim that the limit superior Rn Sn is equal to r, remember the limit of the Rn, times the limit superior of Sn. Okay, so to perform this proof, let's let S equal the lim sup Sn and let T be the lim sup Rn Sn. So limit supremum, or limit superior Rn Sn is this object over here, right? And then over here we have r times the limit superior of Sn. So limit superior of Sn is this object right here. So the left hand side is t and the right hand side is r times the value of s. So we'll prove that these are equal by doing a less than or equal to argument in both directions. Okay. So first let's aim for rs being less than or equal to t. Okay, let's see if I remember how to do this. Okay, so by the corollary, right? The corollary says that m is inside of here, so by the corollary, what do we get? There is a subsequence s sub n sub k of Sn with s sub n sub k heading on towards s, right? Because remember, s is the limit superior of the Sn's, and this one says that the limit superior is actually a subsequential limit. So I know that there exists a subsequence that actually heads towards s. Okay. Recall that Rn converges to r, so by the theorem at the beginning of the lecture, we know that any subsequence of Rn will converge to r. Will definitely converge to r. So that means that Rnk, Snk, Snks go towards s, and the Rnks are forced to go towards r. So this particular subsequence is definitely going to go towards rs. Right? So what does that mean? So rs, which is r times s right here, is definitely going to be less than or equal to the limit superior of Rn Sn, right? Because this was a subsequential limit. So if it's a subsequential limit, it's less than the limit superior, because the limit superior is the supremum of all the subsequential limits. And what was lim sup Rn Sn? Well, that was just defined to be t. Right? So in other words, rs is less than or equal to t. Halfway there, t now needs to be less than or equal to r times s. Okay, so let Rnk Snk be a subsequence of Rn_Sn that converges to t. Right? Remember that t was the limit superior of Rn_Sn, and we know that the limit superior of Rn_Sn is an actual subsequential limit because we showed that in this corollary. So let RNSK SNK be an actual subsequence that converges to T. Okay, we know R is positive, so in particular it's not 0. So the limit of SNK will be equal to the limit of RNK SNK over RNK, and that's just equal to the limit of the top, which remember is T, and the limit of the bottom, which is just R. Okay? And remember that the limit of SNK, well, that's actually just S. So thus, what do we get? We get that T over R is going to be less than or equal to S, because limit of SNK is a subsequential limit, and remember that S was the limit superior. It's the least upper bound on all of the subsequential limits. So this T sub R monster right here is definitely going to be less than or equal to S. But then, what does that mean? Multiply both sides by R, and you get that T is less than or equal to RS, as needed. Alright. So therefore, conclusion overall, looks like T equals RS, and we are done with the proof. Okay, as a final note here, the definitions of limit inferior and limit superior can be extended in a very natural way to include two of our favorite numbers now, the positive infinity and the negative infinity. These would of course be relevant to the unbounded sequences, and you'll get a few homework problems that start to play with that. Okay, your homework this time, should you choose to accept it, is problems 1, 2, 3, 4, 10, and 17. So take a glance at them and see if we can have a fun time on Thursday talking about them.